Thank you for the introduction. Indeed, but before I'm going to talk about that, I'll give you an introduction to measurement error and misclassification. So measurement error or misclassification, which is concerning binary variables, may bias the estimates of parameters even when the error is entirely random or independent. People often think that it's always guaranteed to be attenuation towards a null, but this is only the case when the misclassification is non-differential, when the exposure has no more than two categories, so no multinomial or ordinal, and all covariates are measured without error. And even then, it's quite difficult to quantify the bias when a covariate is measured with error, especially when there's multiple covariates. And in the extreme case, with extreme misclassification, the sign of an observed association can be reversed. Now, if we go to IPD meta-analysis, we must consider that there may be different measurements used across studies. Now, and if one of them is less accurate than the other, you could say that in that case, the gold standard is missing, meaning it is prone to misclassification. And also, this may introduce heterogeneity in the exposure outcome effect. Now, further, when we're performing an IPD-MA, an individual participant data meta-analysis, we should account for clustering of individuals within studies, and we should allow for heterogeneity of the effect of interest. This means that traditional methods for misclassification cannot really be applied in IPD-MA, as they assume that the misclassification rate is transportable to other studies. Now, this assumption is only really tenable when the measurement instruments and protocol and so forth are exactly the same across all of the studies in the IPD-MA, which is very rare. So what we should do, we should apply a method that accounts for possible heterogeneity across the studies in misclassification, exposure prevalence, outcome prevalence, and the exposure outcome association. Now let me give a fictional but real clinical IPD-MA example. This is based on data that's gathered by the IDAMS consortium. So the outcome of interest is the presence of dengue virus versus other febrile illnesses. And we assume this is always correctly classified. The exposure is muscle pain, to keep it simple. And we have two measurement methods. One is always observed but maybe misclassified, and the other one is always correctly classified but maybe missing in some studies. We have a covariate joint pain, which is always correctly classified. Now we can put it in a diagram like this. We want to explain dengue on the right, and we do that using muscle pain and joint pain, but muscle pain it may be missing, the blue circles may be missing. So what we have in those cases is the muscle pain with star, the possibly misclassified exposure. Now, this seems like it's quite a complex problem, and for frequentist methods it is, but in Bayesian analyses, we have a very general solution to this, which is actually quite easy to implement. That's because it fits three submodels: an outcome model, an exposure model, and a measurement model. And each of those models can just be a logistic regression model because they're all binary variables. So to start with the outcome model, this is just a logistic regression, which I'm sure you're all familiar with. We model this using an overall intercept, random intercepts. We have a beta for the covariate effect and for the exposure of interest, and a random effect for the exposure of interest. And then G is the lung function, so the logistic function. And throughout the presentation, we apply normal priors for coefficients and inverse gamma for variances. Then we have the exposure model. This is also a logistic regression model where we attempt to predict the true value of the gold standard exposure using intercepts and the covariate, so joint pain. And then finally, we have a measurement model that aims to explain the misclassification in the possibly misclassified exposure. We stratify this by values of the gold standard because we don't want to induce an association between the sensitivity and the specificity of this relationship. So that brings us to this diagram of the model. All of the arrows have a coefficient, and we've also introduced these two arrows here, the interaction between muscle pain and joint pain, because the effect of joint pain may depend on the true value of muscle pain. Now, so far we've assumed that the error is non-differential. That means that the error does not depend on the true value of the gold standard, of the outcome. But it might be the case, of course, that this misclassification is dependent on the presence of dengue. So we can also add the outcome to the model, or alternatively stratify the model by Y. That is the measurement model. We apply this to the clinical example using the data that is similar to the data from the IDEMS consortium. We have 700 participants per study and 10 studies, and we apply 5 models. First of all, we have a model that takes all of the data, even the data that is missing. Then we have a complete case analysis that only uses the studies for which we have the gold standard. Then we have a naive model which uses the misclassified covariate exposure when the gold standard exposure is missing, and we have the misclassification models. If we look at the results here, if we focus on the beta, the true value in this case is 0.87. The complete case analysis overestimates it in this case, and the naive model greatly underestimates the beta. And both of the misclassification models are closer to the true value. Now, this is just one case, of course. So we also did a simulation study where we repeated this 1,000 times. The only difference is that we only have one misclassification model here, the non-differential one. And it's actually over-specified in this case. So now the true value for beta is 0.80. As you would expect, the complete case analysis actually does get the right value here. But the root mean square error for the complete case analysis is much larger than that in the full data or in the misclassification model, which also has a correct value for beta. And the naive model grossly underestimates this value for beta. It also has a very large bias. And as you would expect, the complete case analysis and misclassification model have practically zero bias. And then finally, the power for the misclassification model is the highest for the ones, except for the full data, of course, which we don't have. And the coverage is behind the frame here, but the coverage for the naive model is bad, of course, and the complete case analysis coverage was lower than the misclassification model. So the key findings are that the Bayesian estimation framework is very flexible, and it allows for adjusting patient-level sources of measurement error. This is most effective when we're interested in multivariable models, so either prediction research or causal research in observational data, because we tend to have a lot of covariates there. And we can adjust for this measurement error either on the data set level or on the patient level or both. And finally, because we have so much data sometimes in IPD-MA, we can allow for overspecification of possible measurement error and heterogeneity of prevalences or of exposure outcome associations. So finally, this project has received funding from the EU, and we thank the IDEMS consortium for providing aggregate data. Thank you.